In this lesson, we're going to talk about applications of functions to economics. Let's start off with the cost and revenue problem. The cost function gives us the total cost when we produce some quantity of a good. This is different from the cost per item. This is the total cost. So when we produce Q items, C of Q tells us how much it will cost us. With that said, would you expect this function to be increasing or decreasing? Well, remember, this is not the cost per item. This is the total cost. So if you add another good, you have to pay something for it. It will be going down in cost per item. There's how you could become more efficient and pay less per item. But each item costs something. With that said, the cost function is an increasing function. The total cost goes up as you produce more. Here's a starting example. A factory that makes radios has a startup cost that you have to pay no matter what. This is the case for most things that you begin. You have to pay some sort of money up front. And then you have other costs, labor, materials, different things like that. These are what we call variable costs. These costs will occur per radio instead of being something you have to pay no matter what. So let's suppose that we have the fixed costs being $24,000 for this company, and then the variable cost would be $7 per radio. We want to write a formula for the cost function. Now this is describing a linear function, so let me give you a way that this could be set up in general for cost functions that are linear. C of Q is equal to the fixed costs, which is like your B that we talked about before, plus the variable cost, which is like your M that we talked about before, times Q. So if we simply plug these in, we're going to have C of Q. The fixed costs were $24,000. The variable cost was 7, and that's all. That's our cost function. Now, I mentioned earlier about this efficiency thing where the cost per item could get lower, but the total costs are still rising. This cost per item is what we call the marginal cost. We're going to make this definition better later, but right now let's just call the marginal cost that variable cost to produce one additional unit. If you're looking at a linear cost function, this is just going to be the slope of the cost function. But in general, this is something that we may sometimes see decrease over time. In addition, the y-intercept when you draw these things would also be your fixed cost. Let's graph the cost function from the previous example. Again, it was C of Q equals 24,000 plus 7Q. This is a linear function, and it looks like our scale is going by thousands. This is on the Q-axis, and the 15,000s on the C-axis. When you plot a line, we'll start off by doing 24,000 as our y-intercept. The next tick mark is 30,000, so 24,000 will be somewhere around here. And then we're just going to rise 7 at a time. And really, I'm going to go up 7,000 when I go across 1,000. So 7,000 up from 24,000 is 31,000, which is about right here. And then 38,000, 45,000, and 52,000. You'll notice this is a nice linear function. I'll just draw the straight line through them. Let's look at a few other examples of just what it would look like if we were to do other forms of this problem. Let's suppose our fixed costs are large, but the marginal cost is small. What that would mean is I would have a very high y-intercept, maybe somewhere up here, but a very small slope. Or I could have something with no fixed costs, but a very high marginal cost. That would start at the origin, but go very high very quickly. You'll notice that after about the third tick mark, I've already had this second example go higher in the total costs than the first one. So even if you have to pay a lot up front, if your marginal cost is small, eventually that is going to be a good thing. Watch out for schemes where they say no upfront costs, because chances are the marginal costs are very high. Next is the revenue function. The revenue function is based on how much is sold. The more that you sell, the more money that you make. And a lot of times the revenue function can be described by a single equation. Let's suppose you have a set price per unit and you sell Q units. Then you arrive at this equation. Simply take the price per unit times the quantity sold Q and this is your revenue function R of Q, where Q is again the quantity that we had before. Notice that whenever we have it like this is actually just a straight line that goes through the origin. You don't get any starting revenue. You have to sell to make money. For our example, let's take a look at these radios that we're going to sell for $15 each. The function is pretty straightforward. The R of Q was just P times Q. Well, P is your set price of $15 each. So we have 15Q. And that's it. All we have to do from here is just draw the equation of the line that passes through the origin and goes up by 15,000 for every 1,000, which is pretty nice on this scale. Now here's one of the fundamental things when we're looking at cost and revenue. Let's graph both of these on the same axes. Now take a look at this graph. Notice that the revenue is rising faster than the cost and eventually overtakes it. That's a very important part of cost and revenue analysis. Now it appears that they intersect at 3,000, but let's do a careful calculation to check this. To do that, I'm going to set my cost and my revenue equal to each other. If we solve this, let's subtract 7Q from both sides. This gives us 24,000 on the left side and 8Q on the right side. We'll divide both sides by 8, and that gives us the answer that we expected. Q equals 3,000. In the context, this would be radios. So once 3,000 radios are sold, the revenue is now higher than the cost, so the company's making money. As our final answer, the company makes money when they sell at least 3,000 radios. Here's the last part. The profit function is what we call revenue minus cost. It's basically the idea of take the amount of money that you're bringing in, subtract off the money that you are spending, and that's the money that you actually get to keep, money that you've earned in the process of running this business. It's different from the revenue in that the revenue is all the money you bring in, and the profit is all the money that you get to keep after paying your costs. We use the letter pi so as to not cause any confusion with P. P was price, possibly. And so we'll simply write pi is equal to R minus C. Your profit is your revenue minus your cost. Now, this break-even point we actually already found. The break-even point is where you have zero profit, or another way to think about it is when your revenue equals cost. So we actually just found the break-even point a moment ago. That's the formal term that we use whenever your cost and your revenue now are equal, so that your revenue is going to overshoot the cost and you make a profit. Let's find a formula for this profit function. We're going to call this thing pi of Q, and remember it's revenue minus cost. Our revenue function was 15Q, and our cost function was 24,000 plus 7Q. Now I put it in parentheses because I'm subtracting the whole cost function. That's important in order to make sure you get the right answer. Now let's distribute the negative sign, which makes the 24,000 and the 7Q negative. And then I'm just going to combine my like terms with the 15Q and the minus 7Q. That gives me that my profit function, pi of Q, is equal to 8Q minus 24,000. Now let's graph this function. It starts at negative 24,000, which is about right here. And then we're going to rise 8,000, which puts me at negative 16. And then we get to negative 8,000. Then we get to 0, and we just continue going upward. This function represents the profit. And you'll notice at 3,000, that's when the profit hit 0. That's exactly the number we came up with the break-even point in the last slide when we set the revenue and cost equal to each other. For all the values after 3,000, you'll notice the profit function lies above the x-axis. For the next example, we're going to try to do this break-even when we're dealing with table data. Remember, the break-even point is going to happen when the revenue and the cost are equal, which we can spot by looking at the data. You'll notice that around 800, the cost is just a little bit above the revenue. But then by 900, the revenue is higher than the cost. And as a matter of fact, it was 100 higher at 800 for the cost, and 200 higher for the revenue at 900. What that means is it's probably closer to 800 than it is 900 where this occurs. I'm going to give an answer of about 830 units. If we were to try to make this a linear function, we'd probably get 833 and some decimals, but I'll just say about 830. Closer to 800 than it is 900 because the cost was closer to the revenue at 800 than the revenue was above the cost at 900. Next, let's find the company's profit if 1,000 units are produced. Profit equals revenue minus cost. So at 1,000, we'll just look in the table. At 1,000, the revenue is 8,000 and the cost is 7,500. Let's just plug that straight in. 8,000 minus 7,500 would give us a total profit of $500. Now the final question of what price do you think the company's charging for its product? Remember, R equals PQ was one of the equations we used. So if we want to know what the price per item is, we could probably just use the data in the table and align it to the R equals PQ. If we were to divide both sides by Q, notice we get P is equal to R divided by Q. Let's just look at the very first value in the table. The first revenue is $4,000, and we're dividing by 500 units, and that gives us that it is $8 per item. Just like the marginal cost, the marginal revenue and the marginal profit, we can look at this to be refined later, but they would be the revenue and the profit that we get as we produce one additional unit. For linear functions, these are again just slopes. So to put it together with our radio example, we had the marginal cost was $7 per unit. That's how much it cost them to make the radio. The marginal revenue was $15 per unit. That's how much they were selling the radios for. And then the marginal profit was $8 per unit, which is how much money they were making for each radio they sold. And by the way, it is true that the marginal profit can be found by taking the marginal revenue minus the marginal cost. For our second major topic among applications to economics, let's discuss supply and demand. Supply and demand is an amazing topic that drives the free market that we in our capitalistic society consider. When something has high demand but low supply, people buy up the stock of it and resell it for far higher than what it's worth. This is one of the problems with supply and demand. The price point that's selected just doesn't meet how many are being created, and that causes problems with the prices. The idea of a supply curve is that given a price that the item can sell for, manufacturers are willing to create a certain amount of that product. The higher they can sell it for, the more they're willing to make. The demand curve is related to the consumer. Based on the price that the item will cost them, consumers will want so many of this item. The higher the price, the fewer people will want it. Let's mark a few points on these charts. For this P0 here, this is when the quantity is 0 and the price associated with it. At this one, if the item sells for this low, suppliers will not produce it. Now let's look at the similar one in the demand function. This is again for a quantity being 0 and the price associated with it. If the item sells for this high, nobody will buy it. And now one more point on the chart. This is one when the price is 0. If the price is 0, this is the quantity associated with the price being 0. This many items will be demanded if the item is free. Now that might be a kind of strange thing to think about. If something's free, people would get all they can of it. Well, listen, they will get all they can of it. So at some point there will become a place where there's just no reason to get any more, even when the item is free. And then there's certain items that people don't really want in the first place. If I offered you free garbage, would you want a lot of free garbage? But if I offered you free gold, well, eventually even you could get to the point that, I got so much gold I don't want anymore. Not only would the value of gold go down, but that's a different story. Now, just like with cost and revenue, when the supply and demand match, that's another magical point. This is what we call the equilibrium point. This is where the supply and demand curves intersect. It's the place where the supply meets the demand. The price is the perfect point where the quantity supplied meets the quantity demanded. You don't have too much supply, you don't have too little supply. We often use the variables P star and Q star to refer to the equilibrium price and quantity at that point. When the price doesn't meet this equilibrium price, we end up with either a shortage or a surplus, neither of which are great for the free market. Let's do an example. Find the equilibrium price and quantity for the following supply and demand functions. What we're going to do is set these equal to each other. 3p minus 50 is equal to 100 minus 2p. And I'm just going to solve for the price. Let's start off by adding 2p to both sides. That gives me 5p minus 50 is equal to 100. Then we'll add 50 to both sides. That gives me 5p equals 150. And then finally divide both sides by 5, which gives me p equals $30. And let's call this p star. This is the equilibrium price. So at $30 per item, the supply and demand are equal. Now, what about the equilibrium quantity? We need to plug it back into one of these two equations, and it actually doesn't matter which one. Feel free to plug 30 into both equations and see that you get the same answer. I'll choose the supply equation. I'll do S of 30, which would be 3 times 30 minus 50, and I get 40. What are my units? Well, it's not really specified, so I'm just going to put units as my units. Whatever's being sold is your units in this case. Here's an example of how we can write our demand function. Many applications will look something like this. A company finds the average number of people attending a concert is 75. 75 people at the concert when the price is $50 a person. If they reduce that price to 35, the average number of people is now 120. This is exactly how demand functions work. If you lower the price, you increase the demand. Let's use this to write demand. Q is a function of P. Remember this Y is a function of X I mentioned to you before. So when I'm thinking about it as Y is a function of X, that means my price is my independent variable, and my demand is my dependent variable. Let's write 2 points based on our first sentence. Your price is 50, and your demand was 75. For the second sentence, your price was 35, and your demand was 120. We're just going to treat this like a linear function, so let's find the slope. 120 minus 75 over 35 minus 50. I get 45 over negative 15, which is negative 3. You shouldn't be surprised to see a negative slope on a demand function. Now let's use our point slope formula to write the equation. Now remember, P is like X and Q is like Y, so I'm going to translate my formula. It would normally be Y minus Y1 is equal to M times X minus X1. But I'm using P's and Q's, so this is going to be Q minus, I'll use the first point, 75 equals my slope of negative 3. My X is my P in this case, minus the corresponding 50. Distributing my negative 3, I get negative 3P plus 150. And then I'm just going to add 75 to get Q equals negative 3P plus 225. That is the demand function. Now we're also asked to write a revenue function. Remember, the revenue function is nothing more than PQ. So let's take P, which I don't know, but Q I have an expression for it. I'm going to take the negative 3P plus 225 from the demand, and I'm going to put that in place of my Q. And then if I simply distribute my P, I get negative 3P squared plus 225P. And that is my revenue function. In particular, the question also asks what kind of function is this? A function that has a square in it like this we'll often call quadratic. In the next slide, we're going to do a little bit more with this equation. If you have a quadratic function of the form ax squared plus bx plus c, then we can actually find a maximum or minimum value occurring at x equals negative b over 2a. This is a useful formula to have. If your a is negative, if you know anything about quadratic functions, that means it opens downward. Consequently, that's a maximum. If a is positive, your function would open upwards, and that's a minimum. Here's our revenue function from the previous example. If we want to find where the maximum revenue occurs, we're going to do p is equal to its negative b over 2a. Your b is 225, and your a is the negative 3. So I'm going to do negative 225, because it's negative b, over 2 times negative 3 for my 2a. That gives me $37.50. That is the amount of money that we should charge to maximize the profit for this concert. Now let's draw the graph. Just to give you a quick introduction to how we'll graph quadratic functions, I'm going to start off by finding some x-intercepts. I'll do that by setting the function equal to 0. Then I'll factor it. I can factor out a negative 3p, and that leaves me with p minus 75, still equal to 0. Then you set each one equal to 0. When negative 3p is equal to 0, I get p equals 0. When p minus 75 is equal to 0, I get p equals 75. Those x-intercepts will help us draw this a little bit. Let's use a scale of 1,000 for the y-axis, which in this case is your revenue, and 25 for the x-axis, which in this case is your price. Now I'll plot my intercepts at 0, 0, and 75, 0. It also might be helpful to figure out just how high that maximum revenue is. So if you plug that 37.5 into the revenue function to find out just how much money they're making, you'll actually discover it to be $4,218.75. That's another useful point to draw on the graph. 3750 lies right here, and we're looking at about 4,200. So here's our point where we hit our maximum. From there, I'll just draw the quadratic function, and as we discussed, it's going to open downward. And there you have it.